What if the coldest, most forgotten world in our solar system is not actually frozen solid at all? What if, billions of miles from the sun, in a place so cold it should be completely dead, something is quietly burning inside? For decades, Pluto was written off as a lifeless ball of ice drifting alone in the dark. But new evidence, confirmed through NASA's own mission data, tells a very different story. Something deep inside Pluto has been generating heat for over 4 billion years. And what scientists have pieced together about that hidden heat source is stranger than anyone expected. This is the story of how a tiny, distant world, once dismissed as a dead rock, turned out to be hiding a warm, liquid secret beneath its icy shell, and why that discovery is changing how we think about life in the outer solar system. To understand why this matters, you have to go back to what people used to believe about Pluto. For most of the 20th century, Pluto was seen as nothing special, a small, frozen world at the edge of the solar system, so far from the sun that surface temperatures sit around minus 380 degrees Fahrenheit, cold enough to freeze nitrogen into solid ice, cold enough that scientists assumed nothing interesting could possibly be happening beneath its surface. That assumption held for decades, mostly because nobody had ever seen Pluto up close. It was just a tiny, blurry dot, even through the most powerful telescopes on Earth. Everything changed in 2015 when NASA's New Horizons spacecraft, after a journey of more than 3 billion miles, finally flew past Pluto and sent back the first detailed images humanity had ever seen. What those images revealed was nothing like the dead, boring world everyone expected. Pluto's surface turned out to be covered in strange, complex features. Towering mountains made of water ice, massive plains of frozen nitrogen, and most famously, an enormous heart-shaped region now known as Sputnik Planitia, stretching across hundreds of miles. It looked less like a frozen leftover from the early solar system and more like a world that was still somehow active. But that wasn't the biggest surprise. As scientists studied the images more closely, they began noticing something even stranger. Cracks. Long stretched-out fractures running across Pluto's icy crust in patterns that looked eerily similar to what happens on Earth when the ground pulls apart. On our planet, features like this usually mean something. Underneath is expanding, pushing outward, forcing the surface to stretch and crack. That raised an enormous question. What could possibly be expanding beneath the surface of a world this cold? The answer scientists eventually arrived at was almost hard to believe. Water. Liquid. Water, sitting beneath Pluto's icy shell in a hidden ocean that has apparently existed for billions of years. At first, this seemed almost impossible. Pluto sits nearly 40 times farther from the sun than Earth does. It receives only a tiny fraction of the sunlight our planet gets. There should be nowhere near enough warmth out there to keep water in liquid form. And yet, the geological evidence kept pointing to exactly that conclusion. Then, investigators uncovered something nobody expected. Researchers realized that water behaves in a very unusual way when it freezes. Unlike most substances, water actually expands as it turns to ice rather than shrinking. This meant that if Pluto once had a liquid ocean beneath its surface and that ocean slowly began freezing, over time, the resulting ice would expand outward, stretching and cracking the crust above it, creating exactly the kind of fracture patterns New Horizons had photographed. This was a huge clue. But it still left one massive mystery unsolved. If Pluto really did have liquid water hidden inside it, what on Earth, or rather what off Earth, could possibly be keeping that water from freezing solid out in one of the coldest regions of the entire solar system? The truth was even more shocking when scientists dug deeper into Pluto's structure. Unlike Earth, Pluto has no sun close enough to warm it. It has no thick atmosphere trapping heat. What it does have, however, is a rocky core, buried deep beneath thousands of miles of ice, made up of materials very similar to what forms the rocky planets closer to our sun. And rock, it turns out, is not simply inert material sitting quietly in space. Rock contains tiny traces of radioactive elements, materials that are naturally unstable at the atomic level. Over unimaginably long periods of time, these radioactive elements slowly break down, a process called radioactive decay. Every time this decay happens, it releases a small amount of energy in the form of heat. On their own, individual atoms release almost nothing, but spread across an entire rocky core over billions of years, this process adds up to something remarkable, a slow, steady, nearly endless source of internal warmth. This is not some strange, exotic form of nuclear power. It's the same basic natural process that helps keep Earth's interior molten, driving volcanoes, earthquakes, and the movement of entire continents across our planet's surface. Pluto, it turns out, has its own smaller version of that same internal engine, quietly running deep beneath the ice, largely unaffected by how far it sits from the sun. But that wasn't the biggest surprise either. For years, scientists debated exactly how this radioactive heat fit into Pluto's history. One leading idea suggested that Pluto started out as a cold, icy body, and only later, as radioactive decay slowly built up heat. inside its rocky core, did enough warmth accumulate to melt a layer of ice into liquid water. Under this theory, Pluto's ocean would have formed gradually, appearing sometime after the dwarf planet itself had already come together. However, newer research, combining detailed computer models with the actual geological evidence captured by New Horizons, pointed toward a very different and far more dramatic possibility. According to this alternative theory, sometimes called the hot start scenario, Pluto may not have started out cold at all. Instead, as material violently collided and clumped together to form Pluto in the first place, the sheer energy of that process could have generated enough heat almost immediately to create a liquid ocean right from the very beginning, rather than waiting millions of years for radioactive decay to slowly warm things up afterward. Under this model, radioactive decay still plays an absolutely critical role, but not as the ocean's original creator. Instead, it acts as the ocean's long-term life support system, providing just enough steady internal heat over billions of years to prevent that early liquid water from completely freezing solid, all the way up to the present day. Scientists compared the fracture patterns visible on Pluto's surface against predictions from both scenarios, the cold start and the hot start. A cold start would have left behind a specific pattern, early compression as the surface first cooled, followed later by expansion once a subsurface ocean began, forming and refreezing. A hot start would look different, showing steady, ongoing expansion of the surface throughout nearly the entirety of Pluto's long history. When researchers examined the actual data, the evidence leaned strongly toward the hot start explanation. Both ancient and, surprisingly, modern extensional features were found across Pluto's surface, exactly what you would expect if the dwarf planet had. It had been slowly, continuously expanding, driven by an ocean kept liquid deep beneath its crust for billions of years. This meant Pluto likely had a hidden liquid ocean almost from the moment it was born, kept alive ever since, not by sunlight, not by any external source of warmth, but by the quiet, invisible power of radioactive decay happening deep within its own rocky heart. And that discovery led scientists to an even more fascinating question. Just how thick is this hidden ocean? And how is it managing to stay liquid for so long, hidden beneath what should be an impossibly thick, impossibly cold layer of solid ice? Estimates suggest Pluto's icy outer shell may be roughly 150 miles thick in places, an almost unimaginable barrier, separating the surface from the ocean hidden below. Despite that enormous insulating layer, and despite Pluto's extreme distance from the Sun, researchers now believe the ocean underneath has likely remained liquid continuously for the vast majority of the dwarf planet's 4.6 billion year history. Some researchers have proposed that the ocean isn't pure water either. It may contain a kind of natural antifreeze, dissolved materials that lower the freezing point of the liquid, working alongside the steady heat from radioactive decay to keep everything from solidifying completely. Scientists studying this have noted that without some additional tidal heating effect, similar to what keeps oceans liquid on some moons around Jupiter and Saturn, the primary heat source keeping Pluto's ocean from freezing really does appear to be radioactive decay happening in its rocky interior. There's another striking clue tied directly to this hidden ocean, one connected to Pluto's massive heart-shaped feature, Sputnik Planitia. Researchers noticed something strange about its exact position on Pluto's surface. It sits almost perfectly opposite Pluto's largest moon, Charon, on the exact far side of the dwarf planet. Scientists calculated the leading explanation connects directly back to the ocean itself. If a genuinely massive, dense layer of liquid water exists beneath that heart-shaped basin, its extra weight could realistically explain why Pluto's crust rotated over time to settle this heavy region into that specific opposite alignment with Charon. In other words, the ocean's own hidden mass may have physically reshaped how the entire dwarf planet is oriented in space, a stunning result if confirmed, and one that further stacks the evidence in favor of a large hidden reservoir of liquid water existing beneath the surface today. As if all of that weren't enough, scientists studying newer images from New Horizons researchers analyzing a region near a crater called Kiladze, located northeast of the famous heart-shaped basin, identified with other compounds, rather than the fiery lava we associate with volcanoes here on Earth. Volcanoes, whether on Earth or on distant icy worlds, require a genuine heat source to become active in the first place. Discovering apparent evidence of relatively recent cryovolcanic activity on Pluto strongly suggests there's more residual heat remaining inside this small, distant world than scientists had previously assumed. Heat almost certainly connected to that same ongoing radioactive decay occurring deep within its rocky core. Some researchers involved in this research suggested that as Pluto slowly cooled over billions of years, isolated pockets of liquid water may have become trapped closer to the surface. Occasional eruptions, they proposed, might actually be tapping directly into those hidden pockets, briefly releasing material from far below onto Pluto's frozen exterior. None of this proves with absolute certainty exactly how active Pluto's interior remains today. Scientists are careful to describe much of this as strong supporting evidence rather than final undisputed proof. But taken together, the fractured surface, the alignment with Charon, the possible cryovolcanic activity, and the underlying physics of radioactive decay all point toward the same conclusion: Pluto is far from the simple, dead, frozen world it was once assumed to be. So what does this all actually mean, beyond simply reshaping our understanding of one small, distant dwarf planet? It means scientists now have to seriously reconsider what other worlds might be hiding in the same dark, distant region of space. That some of these other distant worlds may have done or are still doing exactly the same thing. That raises one of the most exciting and unsettling questions in modern planetary science. If liquid water can exist, hidden and insulated, on small, icy worlds far beyond where anyone ever expected it, kept warm not by starlight, but by the slow decay of radioactive atoms, could similar hidden oceans elsewhere in our solar system, or even around other stars entirely, provide the right conditions for life to exist, protected deep beneath the surface, shielded from radiation, extreme cold, and asteroid impacts happening far above? Scientists are careful here too. There is currently no confirmed evidence of life, or even the basic chemical building blocks needed for life, existing inside Pluto's ocean. That remains firmly in the realm of possibility, not confirmed fact. But the discovery that a small, distant world like Pluto can sustain warmth and liquid water for billions of years, using nothing more than the internal decay of radioactive elements, has fundamentally expanded where scientists believe conditions for potential habitability might exist across our solar system and beyond. For a world once considered too small, too cold, and too far away to matter, Pluto has quietly forced an entire field of science to rethink some of its most basic assumptions. It began as a faint, distant dot, barely visible even through our most powerful telescopes. Then it became a fully mapped, richly detailed world, thanks to a single spacecraft's brief flyby in 2015. And now, through years of careful analysis of that same data, Pluto has revealed something almost poetic, a tiny frozen heart, warmed quietly from within. The next time you look up at the night sky, remember that even the coldest, most distant, seemingly lifeless corners of our solar system might be hiding something warm beneath the surface, something that has been quietly burning away in complete darkness for over 4 billion years, entirely unnoticed, until now. What do you think this hidden ocean means for the search for life beyond Earth? Let us know in the comments below. If this story changed the way you think about Pluto, make sure to like this video and subscribe for more incredible true stories from across our solar system.